Hi and welcome to another episode from Spiral Physics Education. So in this episode we're going to be looking at the ear and how it works, but focusing on the role that the cochlea plays in being able to identify different frequencies from the sounds that we're hearing and how they're sent to the brain. And it would be really helpful if you knew prior to this lesson what a wave is, also what a longitudinal wave is, the relationship between frequency and wavelength, and the wave equation. And if you're unsure about any of those, do check out other videos on the channel to help you get up to speed. So let's start with different parts of the ear in which play a vital role in us being able to hear sounds. So first of all, we've got this thing on the outside called the pinna. And the pinna is just a lump of cartilage that channels or funnels sound into the ear canal, which is a tube that links the outer ear into the middle ear and allows sound waves to then travel to something called the eardrum. So the eardrum is a thin membrane, a thin piece of skin that absorbs the vibrations of the sound waves in the air, and it turns them into vibrations from physical vibrations or mechanical vibrations on that membrane. And the eardrum then is physically attached to the smallest bones in the body, called the ossicles, and those ossicles then transfer the mechanical vibrations onto something called the cochlea, which is this coiled part of the ear. Also attached to the cochlea part of the ear, there are three semicircular canals, which you can see at the top in the purple area. They don't play a role in hearing, but they're to do with balance. So if you ever get an ear infection and you feel a little bit unbalanced, that's why your ear helps you balance. So the role of the cochlea is to transform all of the sound waves, the mechanical vibrations, into electrical signals, and those electrical signals then travel along the auditory nerves to the brain, and you hear sounds of different frequencies. So just to summarise that for your own notes, here we have the pinna and what role the pinna has, and the ear canal, and the eardrum, and the ossicles, and the cochlea, and the auditory nerves. So what we're going to do, we're going to concentrate on the role that the cochlea plays, because it's quite a complex little device that helps us hear different frequencies and differentiate between those different frequencies. And there are two main parts to the cochlea that we're going to focus on. And the two main parts, well, the first part is it contains a fluid. So when the vibrations from the ossicles are passed on to the cochlea, the fluid in the cochlea sends a wave backwards and forwards through that coiled part. So that's the first thing. There is water in there that has a wave that moves along that coiled part of our ear. So the next thing is there's a membrane, and the membrane is inside the coil part again, and it's affected by the wave that travels along the fluid. And that has different thicknesses, so it's got thin parts and it's got thick parts, and the thickness determines how sensitive it is to different frequencies, and that's how the cochlea helps us differentiate between different frequencies. So here's my attempt at drawing the cochlea, and as you can see at the base it's very, very thin, so we can't fit much. We can only fit small waves along there, so small wavelengths, so they're going to be high frequency waves. So we've got at the base a thin base and therefore small wavelengths, or high frequencies. That's where we're going to be sensitive to 20,000 Hertz frequencies. And you can see there that the apex, it's much thicker, and if it's thicker we can fit a longer wave along there, and longer waves means lower frequencies, and that's where our 20 Hertz sounds are sensitive and picked up. And just to remind you then, The thicker the membrane, the longer the wavelength. And if we have a long wavelength, that means we've got a shorter or smaller frequency. So let's stretch out this membrane so that it's flat, so you can see it's in a little bit more detail. And therefore you can see that the apex is much wider than at the base. And if it's much wider, therefore you can fit it in. The wave is going to be longer because it's wider. And that's where that 20 hertz is being able to fit in, that longer wavelength. And at the thinner end, at the apex, it's much smaller, and therefore the wavelength is going to be smaller, and therefore the frequency is going to be higher. Okay, and that's what you need to be able to remember, is that the thickness is linked to wavelength, and that wavelength is linked to frequency. So if it's thicker, the wavelength is longer, the frequency is smaller. Now, along the membrane there are hairs as well, but as you can imagine that before we get onto the hairs, the different parts of the membranes, it goes from thinner to thicker, so different sections between those thick parts where it's sensitive to 20 hertz and the thin part where it's sensitive to 20,000 hertz. You've got all different lengths of thicknesses of membrane, and therefore you've got areas which are all sensitive to different sounds of different frequencies, and that's why our human hearing range stretches from 20 hertz to 20,000 hertz. It's because this membrane is sensitive between 20 and 20,000 hertz. So you can imagine in animals that have a much wider range of hearing in terms of frequencies, you can imagine what their cochlea would look like. It would be much thinner and much thicker if they had a wider range. So if they're able to hear lower frequencies than 20 hertz, you're going to need a thicker membrane. And if you can hear higher sounds than 20,000 hertz, you're going to need a much thinner membrane at the apex. So it's all about what's happening at the cochlea. So along this membrane there are hairs, and those hairs are excited when the membrane vibrates. So if a certain part of the membrane vibrates, then that hair will vibrate, and that will stimulate some sound waves, an electrical wave, electrical signal along the auditory nerve to the brain. And that's how we end up hearing different frequencies. So different hairs vibrating at different positions along the membrane will send electrical signals to our brain about different frequencies. So it's all very complex, but it's all to do with a stretched out piece of membrane with hairs on it. So I hope that you found this episode on sound and the ear useful. Don't forget to subscribe to the channel to check out different videos on physics that I'll be posting, and hopefully they'll help you understand physics in a little bit more detail and boost those grades for you. And we'll see you next time on Spiral Education Physics. Goodbye.